exchange of funds basis, if they become a partner with us, it facilitates their getting the resources within their own country to develop whatever kind of program they wanted to develop that's relevant to what we do. Perhaps it's investigating the moon, or in the case of Korea, they're very interested in going to the moon with the mission themselves. Whatever the country's interest is, if it relates to what we do with our domestic team, we are happy to entertain a proposal from them, and so far 8 of them have been accepted into our international family. And then we urge cross-collaboration between the domestic teams and the international partners, and that's going really well. This is a distribution of where the principal investigators and the co-investigators are just for the domestic teams. And again, just to give you an idea that there are a total of 318 researchers, including the students. There are many students that are involved with these teams. And the average team size is roughly 30. We have one that's up to 60 number. Okay, so getting down to more details about what these teams actually do, I've selected just a few research highlights. They have many. I mean, each one of these teams could easily take up an entire hour just to tell you the fascinating work they're doing. But let me just give you a few highlights. So Dan Brett at the University of Central Florida has a team called the Center for Lunar and Asteroid Surface Science. And they study the physical properties of regolith, of dust that we talked about on the surface of bodies like the moon, but also asteroids and moons of Mars. The geotechnical properties, the microgravity effects that you might encounter, impact ejecta, dynamics, hydration and weathering of the near-Earth asteroids. Over time, the 4.5 billion years that these bodies have been in space, there's been a lot of weathering that's happened. And the charging and mobilization of dust on the surface of any of these is going to affect any machinery you're going to put there, and certainly the astronauts themselves. So then the next one, Andy Rivkin, the Applied Physics Laboratory at Johns Hopkins University. Their team is called Vortices. Very long name, and NASA loves its acronyms, so you can see how they developed vortices out of their name. But they study volatiles, regolith, and thermal investigations. They look at the sources, sinks, and processes, and the interaction that various materials will have with the regolith, and the evolution of that dust on all of the target bodies. Okay, the group at the Goddard Space Flight Center, led by Bill Farrell, this is called the Dream 2 team. And the reason it's called Dream 2 is because Dream 1 was part of the NASA Lunar Science Institute, which I was also the director of in the last couple of years before it transitioned into Survey. So I got to know the teams from the NASA Lunar Science Institute pretty well, and I was really pleased that when we had our peer review process of the proposals, it turned out several of the principal investigators who had been leading teams under the Lunar Science Institute were selected for Survey. So Bill Farrell was one of those, and the dynamic response of environments at asteroids, the moon, and the moons of Mars is what he calls Dream 2. They studied plasmas. The plasma interaction that comes from the solar wind. When the solar wind comes and interacts with a body like the moon, it does a number of interesting things. And the fact that we now see OH all over the surface of the moon, and the solar wind contains hydrogen as it's traveling and runs into the regolith on the moon, you can see how the H and the OH can get together and form water. So the plasma processes as they interact with the moon and the other bodies are very important. And you can also see here that we have the solar wind charging of asteroids. This is something else that they study. They model this. We have a lot of interesting results that show the kinds of things that you need to think about when you're looking at the charging from these kinds of interactions. Timothy Glotch from Stony Brook University has a team that they call the RISE team, and they do the remote sensing of airless bodies, field operations, and metrics for human exploration. They look at the reactivity and the toxicity of regolith. These can be dangerous to humans. So, when the astronauts were on the moon, the spacesuits were just covered with dust. And getting back into the vehicle, this is a concern because if you're breathing in that dust, it turned out it was a very sharp, jagged kind of material, and it can be really, really harmful over a long period of time. So they look at that and try and understand what we have to mitigate against. They also do synchrotron analyses of samples, and they look at volcanic and impact crater analog research, which means you go to places on the Earth that look like good analogs for places you want to go in space, and you try out some of your machinery and some of your techniques to see how they would best work. Okay, continuing on, Mihai Harani from the University of Colorado, his institute team called IMPACT has developed the world's fastest dust accelerator, and this is open to the entire scientific community and exploration community so that people can take samples there, they can try out new experiments, and it's really going well. They're doing a lot of phenomenal work, and they have just built a new ion gun that simulates the solar wind so that they can extend this research even further. And here you can see the penetration and the charging studies that they do as well. Carly Peters from Brown University, her team does a lot of interesting stuff with the evolution and environment of whatever destination we're going to go to. But I'd like to really highlight the work that they've done on the moon, because I think one of the most exciting results that we've learned about the moon is the fact that it's so wet. Now, it's wet compared to what we thought it was. It was so dry. A few years ago, we thought we thought it was very dry. And it's maybe about as wet as the Sahara Desert, but that's still a lot wetter than what we thought. So to put it all in perspective, but the water is in very different locations, and that indicates it came from probably at least three different sources. And the one that we found inside the crater when we had the L-Cross mission, I'm sure many of you will remember that a few years ago in 2009. This was a mission that went to the moon, deliberately crashed into a crater, kicked up, excavated a bunch of material, and then studied what the composition was. The L-Cross mission, which was developed at Ames, revealed that we had water ice at the bottom of the crater, the Cabeus crater. Well, that was great confirmation. We were all very excited